on the screen. Just a sec. So we talked about work done by isothermal and adiabatic. I gave you some important formulas for integration methods. Okay. Then we talked about constant volume process CV and then constant pressure process CP, right? And then we talked about something called Mayer's relationship, CP minus CV is equal to R. We talked about quasi-static process, non-quasi-static process. Okay. Reversible, irreversible, we talked about it, right? We talked about some applications of isobaric process such as vaporization and freezing. So you see the atmospheric pressure is constant pressure. So that means when you are boiling, the water molecules are working, trying to, water molecules are trying to expand against the outside pressure, atmospheric pressure. Okay. Same thing with freezing. When you're freezing, the water molecules are trying to become ice, right? So in a way, ice is also increasing in volume. So you would have seen this in some cold countries, right? In the cold temperatures, during the cold temperatures, like minus 20 degrees Celsius, minus 5 degrees Celsius. What they do is they will empty the swimming pool. Okay, if they don't empty the swimming pool, what will happen is the ice will try to expand and it will break the swimming pool. So because of that, during the winter months, they will empty the swimming pool. Okay. So I talked about this vaporization freezing, right? I wanted you to, go through this yourself. Okay, very simple. Just we are doing Vg minus VL. Okay, so as I told you, the last part is Carnot engine. Okay, Carnot is the name of a scientist, French scientist. So what he did was he devised something called like a theoretical engine. So let's try to explain that. So you already know something about isothermal adiabatic processes, right? So we are going to make use of those knowledge here. So in Carnot engine, we assume that there is a insulated cylinder like this. Then there is an insulated piston like this. So the interesting thing is the bottom part is not insulated, right? So which means to say that I can change the base. So this is insulated.
So we need, after this, below this, we will need an insulating stand also.
Yeah, we'll come to that. So if I want to give some heat source, right, very high temperature, then I'll be putting this as T1, okay, very high temperature. But suppose if I want to, if I don't want to give any heat, if I want to put an insulated stand, I can remove this. So this is like an insulated piece here, which means if I put it over here, there is no heat going out. Similarly, if I want a sink, you know what is a sink? So sink means it will, you can dump the heat. So that means this will be at a low temperature. So when you put a high temperature, the heat will be going this way. Okay, so going into this gases. So if I put it on the low temperature sink, what will happen is the heat will be flowing back here this way. So from here to here. Okay. So that's the first thing. So you should understand the construction. The next thing is we already studied this. This is your T1. This is your heat engine, HE. And it's going to give out some heat to the sink, Q2. And this is what is your heat sink, T2. And this will be your W. Okay. If I want to draw the graph for this, the Carnot engine graph will look something like this. So you start from a particular pressure, volume, and temperature, P1, V1, T1, right? If I do an isothermal expansion, what does that mean? If I put some heat over here, right? High temperature sink, high temperature source over here, right? The heat will be going this way, which means this piston will start expanding. So when it is expanding, what will happen is you are adding heat. So the piston is moving up. So the volume is increasing and the pressure is also decreasing, right? Initially the pressure is increasing, but then as the piston is going up, the pressure decreases. The temperature, let's see, 1 to 2, it is isothermal expansion. Okay, meaning the temperature is almost equal to T1. Okay, so this is T1, this is also T1. So just because it's giving some heat here, this will not reduce in temperature. So if this is say 1000 degrees Celsius, the 1000 degrees Celsius will be given over here. So since it is fully insulated on all the other sides, the heat cannot go out. So this is what we call it as heat is absorbed isothermally in this process 1. So it's coming to P2, V2, T2. Or sorry, isothermal, which means it is still the same temperature. So this is isothermal expansion. As I told you, the piston is going up, which means the volume is increasing. Okay, the pressure is actually decreasing. The temperature remains the same. Okay, this is what is meant by isothermal expansion. If you are wondering, sir, why do you have this insulated stand? So that is where we are going to use the next one. So suppose if I put the insulated stand here, right? What will happen is as the piston is going up further, imagine that the piston is going up to a certain extent and then it's still going further. At that time, I'm just putting this. So if it is going up further, what will happen is the pressure will decrease very rapidly because the heat is, there is no heat coming in here, but then, whatever, since this is completely insulated, right? I cannot keep the same temperature because the pressure is decreasing as it is going upwards, as the piston is going upwards, right? The pressure here is decreasing. Since the pressure here is decreasing rapidly, the temperature will also decrease. Okay, this is a bit confusing, not a easy one. So as I told you, it will take some more time. This is one of the reasons why many school teachers they skip this topic. Okay, so this is a little bit of a college level thing. So as you go, of course, if you study it now, even if you understand some 50-60%, when you go to college, it will be definitely useful. So please study, take some effort. Of course, it's useful for your exams also, but I'm just saying the long-term advantage. So let's say initially this piston was going up only to this distance. Okay. So at that time, what I'm trying to say here is the temperature is always kept constant. So if this is T1, this gas will also be at T1 because it's an infinite source. Infinite source means it will keep on giving the heat. But now if I remove this cylinder and put it on the insulated stand, what will happen is this piston will, after being here in the process 1 to 2, now it is at 2. So from here it is going to 3. Now what happened is there is no way of heat coming in here. Okay, so since there is no heat coming in here, the temperature will drop. So it means the adiabatic expansion will look something like this. Okay, so this I'm going to call it as P3, V3, and then T2. Okay, why not T3? Because here I said this is not T2, it's the temperature is remaining the same. But if it is expanding further, right? When the piston is expanding further like this, the pressure will drop. As the pressure drops, the temperature will also drop. But the volume is increasing. You see the volume is further increasing here. So this is your volume and this is your pressure. So this is adiabatic expansion. So the next process is, suppose if I keep this, if I keep this cylinder from third position, right? If I keep it in this sink, low temperature sink, right? What will happen is whatever extra heat you have, that will be dumped inside this one. Okay, which means suddenly the entire thing will come to a lower temperature, which is T2. It's something like the engine valve. As soon as the valve is opened, some 1000-degree, 2000-degree Celsius gases will be suddenly rushing out of the engine, which means the temperature will be dropping soon. But the actual process, right, once it is dropped, the temperature will remain the same, or it's a little bit theoretical here. Okay. So what we are trying to say here is, so the next process will be isothermal compression. So this might be slightly confusing, so pay attention. Let me say that one more time. So when I compress this piston, right? So it's at location 3, and now I'm pushing this in. Okay, as I push this in, what will happen is the pressure will increase. That's what it's shown here because it is compression. The volume will decrease. Okay, which means the volume is coming back here. You see here, this is higher volume, this is lower volume. So the volume is decreasing. But what I'm trying to say here is the temperature in the gas, right? Initially, it's T2, and then as you keep pushing this, if there is some slight increase in the temperature because of the increase in pressure, that increase in temperature will be even out over here, because this is something like a ice, which means the temperature will always be maintained at the same temperature, T2. That means here also the temperature is T2. Okay. At this point, I'm going to call it as P4, V4. And then finally, if I again put this insulated stand in this position, right, from fourth position, if I put it further, I'll be pushing this in. Suppose, let's say this is my fourth position, and if I'm putting this insulated stand. So if you want, I can show that diagram one more time. So suppose if you are here, right, and if you are pushing this further to bring it to the first position, I put this insulator stand, and then I am pushing this further inside. Okay, again the compression is happening, but now what happened was, instead of this sink, right, you have the insulated stand. So what that means is the heat cannot go out. Since the heat cannot go out, the temperature will rise as you compress it. So this is the point which I'm trying to say. Very difficult to follow. So let me say that one more time. When you keep it in the T1 or T2, right, the temperature remains the same, because whatever drop in temperature will be compensated by the heat going from here. Whatever increase in the temperature will be compensated by heat going here. But when you put it in an insulated stand, the heat cannot go in, which means the temperature here will drop. Similarly, as you compress this, the temperature will increase, but then this is insulated stand. Since it is insulated stand, the extra heat cannot come out. Since the heat cannot come out, the temperature will increase here. Okay. So this is very, very confusing. Okay. Adiabatic means heat is not exchanged, but the temperature will rise or drop. Whereas isothermal means there is a heat exchange, but then the temperature remains the same. Anybody following this?
Yes, sir.
Yes. Okay. Others not following? Only 2 people are following.
Following, sir.
So make a note. Definitely, it's going to be a bit confusing. So unless you have proper notes, you will be blinking forever. So in isothermal, temperature constant. But very often intuitively we think that temperature constant means there is no heat transfer. Well, that is not correct. Okay. The temperature was constant because there is a heat transfer. In adiabatic, adiabatic means heat transfer does not happen. So no heat transfer. Since there is no heat transfer, the temperature will change. When you compress it, there is no way the extra heat can go out, which means the temperature will increase. Temperature changes. So suppose if I pull the piston, expansion means the temperature will drop. Compression means temperature will rise. Okay, that's what I tried to explain here. You see, Here, when you're doing adiabatic expansion, the temperature is dropping. Here, when you do the adiabatic compression, you're going this way. Then the temperature is rising. So from T2, this is going to a higher temperature, T1. So this is high temperature. So take it, take it down properly. T1 is high temperature. As I always say, handbook has got all these things, but then, you don't have all these, notes properly. So you have to take down your notes properly. Handbook, the purpose of handbook is anybody who has attended the class, if you have the notes, then the handbook will be very helpful. Okay. If you don't know this class, what happened in the class, obviously you will not understand anything in the handbook. So T2 is low temperature. So these things, it is kind of understood in the diagram, but since you are new to this, you should understand this is higher temperature, this is lower temperature. So this entire thing is T1, this entire thing is T2. So this is adiabatic compression. Okay. So this, by the time you compress this, right, you bring it back to the same point. And this is what we call it as a cyclic process. So this is what Carnot says. So what Carnot says is, if you had a 4-stroke engine like this, then you will have the maximum efficiency. So in other words, what we say here is, remember this Carnot, Sadi Carnot was a French engineer who did this work somewhere around 1800, some 1820 or 1850, I don't know, right? So it's been like more than 150 years or maybe 200 years. And still, whatever theory he gave, it's still valid. So what it says is, whatever maximum efficiency you calculate from this Carnot engine, that is the maximum efficiency that is possible in your engine. You cannot have an efficiency more than that, okay, for a given set of parameters, T1 and T2, temperature. So in the petrol, this T1 is determined by the petrol or diesel, right? Or some other methane or whatever gas you use. So depending upon that, that T1 will be determined whether you have 1000 degrees Celsius or 2000 degrees Celsius or 3000 degrees Celsius is determined by the fuel. T2, of course, is your atmosphere. Okay. So the atmosphere, depending upon whether you are in Chennai or Shimla or Ooty, right, the T2 temperature will change. Okay. Or whether you are in US or Canada, then it will be minus 20 degrees Celsius. If you are in Ooty, probably it will be like 5 degrees Celsius or 10 degrees Celsius. If you are in Chennai, it will be somewhere around say 35 degrees Celsius or 40 degrees Celsius. Okay. So that means the T2 is determined by the atmosphere. T1 is determined by the fuel. Okay. So based on this T1 and T2, Carnot gave a simple formula which says that that is the maximum efficiency it is possible. Okay. No matter how much you work on the engine, right? How much friction you reduce or whatever you do, you cannot have an efficiency greater than a final formula which we are going to derive. So that's the purpose of Carnot engine. Again, I'm just giving you an overall idea. Definitely not an easy topic. Okay. So as you keep on studying this, eventually it will make sense. Okay. But of course, as I always say, understanding the concept is a difficult thing. The mathematics is very, very easy. Okay. Anybody can do it. Okay. Any 10th standard student can do the mathematics. But what is it, why do we have this, what are we trying to say in this diagram? Those kind of thinking is what is the difficult part. So Carnot engine is a hypothetical engine, right? It's not a real engine, but he says that this is the maximum efficiency that is possible, okay, for a given engine which is working between T1 and T2 temperatures. So take it down. which gives the maximum efficiency possible for a real engine working between two temperatures. Okay. So I'm sure it's given in your textbook, but it might be buried inside a lot of paragraphs. So this is the main important purpose of Carnot Engine. So here I'm going to say this is your Q1 going in, heat going in. You see this is Q1. Here it is Q2 going out. I'm going to copy this graph, which is extremely important to write down the. So in the last class, we derived work done for isothermal and adiabatic. Okay. And that is the purpose. So we are going to apply that formulas, final formulas, which we derived into this equation, into this derivation. As you can see, you have only isothermal and adiabatic. So the work done for the first process, right? 1 to 2. This is 3 and this is 4. So work done for 1 to 2, you know that it is isothermal expansion. So if you go back and check your notes, we derive something like mu RT1. Okay, let me go back to this. You see, we derived mu RT ln V2 by V1 for isothermal. For adiabatic, we derived mu R gamma minus 1 T1 minus T2. So this is what we are going to apply here. W12 mu R T1 ln V2 by V1. Okay, so this is isothermal expansion. The second one is 2 to 3. This is adiabatic expansion. So which means adiabatic formula, we studied it as mu R by gamma minus 1, T1 minus T2. Okay. Mu R by gamma minus 1, T1 minus T2. Because the temperature is dropping from T1 to T2. So that will give me the work done. Next one is 3 to 4. 3 to 4 is again isothermal compression. Isothermal means I have to use this formula. W 3 to 4. So for 3 to 4 mu R, you see here the temperature was T1, this line. Here this temperature is T2, which means I should write T2 here. And look at this formula, final volume by initial volume. This was the final volume, this was the initial volume, which means here the final volume is V4, initial volume is V3. I hope everyone is following this. I'm simply applying the formula. If anybody finding it difficult, please stop me. As you should know, the last one is going to be very simple, adiabatic. So W4 to 1. Adiabatic means this formula. Here you drop from T1 to T2, initial minus final here. So here it's going to be T2 minus T1. This is gamma, this is T2 minus T1. Any questions? So the first thing in Carnot engine is understanding this construction. The second thing is understanding this graph and understanding isothermal and adiabatic. What is happening in isothermal, what is happening in adiabatic. And then you have to understand what is Carnot engine, why is it there? Okay. It's a hypothetical engine, so it's not a real engine. Okay, so it's a benchmark. So if I'm making an engine, right, I can tell what is the maximum efficiency that is possible using this calculation. So after understanding this graph, very, very important. After that, writing this equation is very, very easy. Okay. I'll give you a couple of seconds. So please go through it and tell me, sir, I don't understand. So how did this, why do you say this temperature is decreasing? No, why do you say this is constant? You can ask any doubts you have. So please try to take some few minutes. Go through your notes, go through this blackboard. If you have any doubts, please raise it. We'll get some water in the meantime. No questions? Everyone following?
Yes, sir.
Okay. Okay, so let's see. So if I want to find the total work done, right? So I need to add all this work done. Okay. So that will give me the total work done or W net. So that means so before adding, right, I don't want to write everything. So if you see this equations, what you will see is this is T1 minus T2, this is T2 minus T1. This outer values are same, which means to say that this term and this term will cancel. So this term and this term will cancel when you add it, because this will be plus T1, this will be minus T1, this will be minus T2, this will be plus T2. So these two will cancel. So what is left is only this and this. Okay, that means I need to add only this and this. Isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Okay, so take it down properly. So from the values you got, this value and this value T1 minus T2 and this T2 minus T1 will cancel. Okay, so what is left is only this one. So mu R T1 ln V2 by V1 is what you have here. Similarly, for here, you have mu RT2 ln V final. V final is V4 by V3. Yes. So this can also be written as, okay, in ln, you can take this mu RT2 ln V3 by V4. You can write it like this to put a power -1. Okay. So when the 2 power 1 comes to the top, it will become 2 power -1. And you can take the reciprocal with this. So it's the same thing. So when you change this, interchange this, I'll put a -1 in the top. So if I, according to log formulas, you can bring, whatever you have in the top, you can bring it or you can multiply with the same. I told you that, I don't know if I told you in this class or some other class. So logarithm is something like a different world, right? So I think I said it in the last class. So whatever you do multiplication in the real world, you can do addition there. Whatever, a division you want to do, you can do subtraction there. Whatever powers you want to do, you can do multiplication there. Okay, which means you can take the power in the real world, you can take it to the multiplication. Because I'm going very, very slow, okay, so that you don't miss any points. So W net. Okay, so take it down all the steps. Somewhere for efficiency, right? As I told you, we are interested in finding the Carnot engine efficiency. So efficiency for Carnot is equal to W net divided by Q in. Why? Because I told you efficiency is nothing but how much work I got and how much heat I supplied. I want to supply less petrol, but I want to get more mileage. Okay, that is what is efficiency. So that means for W net, this entire term will be coming. Q in, right? So Q in will be, if I go back to the diagram here, the graph. In isothermal, right? So this is your Q in because you're supplying the heat. So you know that in isothermal process, delta U is equal to 0, which means to say that Q minus W is equal to delta U, first of thermodynamics. Delta U becomes 0, which means Q is equal to W. What does that mean? The work done is equal to the Q in. So that means whatever work I did here, whatever I calculated here, that is equal to the Q in. Very simple. Please ask me if you have any doubts. So Q in is equal to the W1 to 2 because this one. So take it down properly. So that means Qn is nothing but W12. W12 is this value. Okay, mu RT T1 ln V2 by V1. We have a separate side derivation. Okay, for now I am going to say that V2 by V1 will be equal to V3 by V4. Okay, from adiabatic relationship. So V2 by V1 is equal to V3 by V4. Sir, how do I know this? Well, we need to do some more derivation. We will do it as a side derivation. Okay, but I want you to complete this main derivation. So if I know that this and this are equal, right, then I can take this commonly out, and ln V2 by V1, if I divide this and this will cancel, mu r will cancel, right? So T1 by T1, it will become 1. Similarly, if I divide this term with this term, mu r will cancel, T2 by T1 will be there. This term and this term are same according to this. Which means to say that I'll be getting T2 by T1. And that is what is the efficiency of Carnot engine. Okay. The textbook, what they have done is, this is a long derivation. So they have just inserted this inside and it looks like a very complicated process. Okay. For now, if you believe me, V2 by V1 is equal to V3 by V4, I can say that, this will simplify into 1 minus T2 by T1. Anybody not following from this step to this step? Please think and let me know if you have any doubts. Ashwant following? Ashwant talking to you?
Yes, sir.
Following? Okay. So what this means is, you see a very complicated expression has been simplified to based on the sink temperature and the source temperature. So you know that T1 is the source temperature and this is the sink temperature. So what Carnot engine says is, you can create a most wonderful engine in the entire world, but still, based on this T1 and T2, that is what is going to determine the efficiency. You cannot have efficiency better than this value. Okay. This is one of the reasons why diesel engine will be having a higher efficiency compared to petrol engine. The reason for that is diesel will give rise to bigger temperatures. When this value is higher, this entire value will be lower. If this value is lower, 1 minus this thing, the overall thing will be, this value will be higher. Okay, so make a note. So thermodynamically speaking, diesel is supposed to give you a higher efficiency. Okay, that doesn't mean that this is true always. Okay, because sometimes it's possible that the diesel engine which you are considering may not have been designed properly, which means the friction might be high, whereas you may have a better petrol engine. Okay, but assuming all the other factors are same, this, the T1 temperature, T1 of diesel will be higher for compared to T1 of petrol. So the efficiency of diesel will be greater than efficiency of petrol. If you substitute this number here, you will understand this. let's talk about cold temperature versus hot temperature. Let's say this is like a winter time, so maybe you have something like 5 degrees Celsius. Maybe this is like a hot summer day, something around say 40 degrees Celsius. Okay, so that's a huge difference. So when you have this, you have like 35 units difference. So which means this value is smaller here. Which means if this value, assuming that the T1 is same, here we assume T2 is constant. Okay, so this is assume T2 is constant here. Here assume T1 is constant. Okay, so take it down properly. If you have all this good understanding, it will be useful for you. So when the temperature is very low here, okay, right, compared to this is cold temperature is going to give you a very low value. If I say this is very low, this value is going to be bigger because 1 minus this small value will give me a bigger value. So efficiency of cold day will be higher than efficiency of hot day. Again, there might be some other factors coming into picture. Okay, like hot air has to be sucked inside the engine, so that may cause negative effects. But thermodynamically speaking, right, if all the other things are kept same, then you can imagine that this is going to be higher. So take it down properly. Okay, sir, this derivation is very, very simple. Okay, if you think it is difficult because you're not studying it properly, if you think it is difficult, okay. So as I told you, this is like a side derivation. Okay, this you can study it separately. So based on the adiabatic expansions, adiabatic relationships, let me check. There is a important adiabatic relationship. I need to find that. Okay, so adiabatic relationships, you have some derivations to be studied. So let's try that. So take it down neatly. Okay, it's not given in your handbook. You know that without proof, I told you PV per gamma is equal to constant. So that's important thing which you have to remember. So maybe in college level, you'll be studying more about this. Another formula which we know is from ideal gas equation, PV by T is equal to constant. But this constant and this constant is not the same. So to differentiate this, I can put K1 here and K2 here. If I want to eliminate P, right? Your mathematics, you must have studied elimination method, right? So eliminate P. So it means you find the P value here and then substitute it over here. So it means P value here can be written as K2 T divided by V. And if I substitute it over here, I'll be getting K2 T divided by V into V power gamma is equal to K1. You see, I don't have space here, so let's make some space. So this will become V power gamma minus 1. This T will come here, or I can keep the T here. K2 will come on this side. So K1 by K2, this is a constant, this is a constant, something like, 5 by 3, 10 by 6, something like that, It can be any number. So which means that is the resulting thing is also a constant. Okay, so that means this is another important relationship. So PV power gamma is equal to constant is one relationship for adiabatic, and this is another important relationship for adiabatic. Anybody not following this? Take it down properly. I'm just simply using this ideal gas equation and adiabatic equation. PV is equal to mu RT is what is converted like this. T comes on this side, mu into R becomes a constant. Okay, so if nobody is copying, I will change the screen.
Sir, I am writing it, sir.
Okay. After finishing, let me know.
Yes, sir, just 1 minute.
So here what I did was I eliminated the P. I can eliminate V also. Okay, suppose if I want to eliminate, you see here the temperature is not there. So similarly, here pressure is not there. So similarly, I want to find a relationship without V. Okay, here also I have V, here also I have V. I want to eliminate V. So suppose if I want to eliminate V, copy it, Kirtan.
Yes, sir.
So another expression V, eliminate V. Okay, so that means you know that PV by T is equal to constant. So V is equal to K2 into T divided by P. But you also know that PV over gamma is equal to constant. In place of V, I'm going to put K2 into T by P over gamma. So this is going to become P power gamma, but when it comes to the top, it will be P power minus gamma. So P power 1 minus gamma. K2 power gamma. T power gamma is equal to constant. I don't like these constants, so I bring it on this side and make one more constant. So this is another important relationship. All the three are the same, only thing it is given in a different form. So this is the first relationship in adiabatic. This is, we are eliminating the P. So that means you get a relationship between T and V. This is, you are eliminating V. So you get a relationship in terms of P and T. So all the three are same. Okay. But all of them are adiabatic relationships. But it looks different because in one case, T is not there. The next one, P is not there. Here, V is not there. Copy it quickly. Simple mathematics. If you're not following, it is your duty to open your mouth. Otherwise, the train keeps going. So now we need to understand how I said V2 by V1 is equal to V3 by V4. So for that, I need to use volume and temperature. Yeah, I need to use the temperature volume, this equation. So I'm going to copy the equation from here again, this graph. Okay, not this one. Okay, listen carefully. Again, we don't want these things. Okay. So we are talking about adiabatic relationships, okay, between V2 and V1 and then V3 and V4. But you may be wondering, sir, that is isothermal. Well, from here to here, there is a temperature drop. So here there is a temperature increase. Okay, so this is V2 T1 and this is V3 T2. Okay, but just now for adiabatic relationships, I told you V power, what did I say? V power gamma minus 1 T. So T into, let me write it in a different color so that you'll understand it better. T V power gamma minus 1 is equal to constant. Okay, that means you see if I apply it for this adiabatic expansion, T is adiabatic expansion means the temperature will change. Yeah. So what this means is T1 V1 power gamma minus 1 is equal to, it will be same for the next process, right? But this is V2 here at this point. So I'm moving from this point to this point. Okay, very important. Please pay attention. So I'm starting from here. So T1 V2 gamma minus 1 and I'm coming here adiabatic expansion, which means I'm going to write this as I'm coming to the temperature T2. So that means T2 and then volume is V3. Okay. Similarly, if I go to this one, right, I'm moving from this point to this point. That means I'm going to write as T2 V4 gamma minus 1 is equal to T1 V1 gamma minus 1. I'm going to write this because I'm interested in finding V2 by V1. So I'm going to rewrite this this way. So T1 V1 power gamma minus 1 is equal to T2 V4 gamma minus 1. This is equation 1. This is equation 2. So if I divide equation 1 by equation 2, T1 and T1 will cancel, T2 and T2 will cancel. So what is left is V2 by V1. Whole power gamma minus 1. Here I will get V3 by V4 whole power gamma minus 1. This goes without saying that if the powers are same, whatever is inside the bracket should also be same. That means whatever I kept it as a side derivation, I finish it. So as I told you, let me repeat it one more time. In the textbook, all these things has been given as one single derivation, which is very, very confusing. Okay. So you should understand what is the main derivation. This is the main derivation. So studying the Carnot engine, and then this is the main derivation. So just, even in the exam, I think you can do it. Okay. So you can simply say V2 by V1 is equal to V3 by V4. So from here to here, it's just one single step. Okay. But then how do I know V2 by V1 is equal to V3 by V4? That's where you have a long derivation here. So you have to start from the adiabatic relationships. So at least you should start from here. Okay. So you should show this part, then derive this. So take it down properly. Simple mathematics, as I always say, mathematics is the easiest part. Okay. But thinking and trying to understand what all these things mean, that is the difficult part. Any questions, any doubts? So this part, I think I have not given it in the handbook. So I just left it as a self-study part. Okay, so take it down properly. Okay, so we are done with Carnot. And there are two theorems on Carnot. Okay, Carnot theorems. So what it says is, as I told you at the beginning, heat engine working between two temperatures T1 and T2 cannot have efficiency more than that of the Carnot engine, the corresponding Carnot engine. So it means you can, do the most wonderful engine in the entire world, but still the efficiency is limited by this formula, which is 1 minus T2 by T1. You cannot exceed this value. So this gives you a benchmark. If this gives you 80%, then there is no way you can make an engine better than 80%. If this temperature values gives you say 40, then there is no way you can improve the engine for these particular temperatures. However, the efficiency of Carnot engine is independent of the nature of the working substance. So what it means is, it doesn't matter whether what kind of working substance or what kind of fuel you have inside, you will get the same efficiency provided you produce the same temperatures. Okay, but in the example which I gave you, the diesel and petrol, I said the temperature produced by diesel is higher, the temperature produced by petrol is lower, and that's why I said the efficiency for diesel is higher. Okay, so that might be confusing, but according to Carnot, it says suppose if diesel and petrol were producing the same temperature, then both will produce the same efficiency. Okay, so it doesn't matter what fluid you have, it will produce the same efficiency. Okay, so very easy, nothing very difficult. Okay, it might look complicated, but you have to practice it before your school exams. Very often they'll ask you this, in the school exams, so be prepared. I'm going to skip this last part alone, okay, because proving the Carnot theorem, it is easy only, but generally this is not given in the textbook properly. Okay, so I'm not sure if they're going to ask you this. So if it is required, you can let me know. Okay, I will teach this. So for now, I'm going to say I'm going to skip this. So I have been going very, very slowly in this chapter, okay, because this is one of the difficult topics.